Good evening. On behalf of our director, General Daly, I'd like to welcome you to the Air and Space Museum. My name is Jim Zimmelman. I'm a geologist in the Center for Earth and Planetary Studies here at the museum. And I thank you all for coming to our final lecture in this year's Exploring Space series. Now, even though it feels like August outside, this was a spring series that we are concluding tonight. Thank you all for coming. And as we say with any of our public events here, these programs are only made possible with the generous contributions from many of our sponsors. And tonight I'd like to express sincere thanks to Aerojet in particular for sponsoring this program, and we are grateful for the very long-term support we have gotten from NASA throughout the years. But tonight in the audience representing Aerojet, we have Joseph Cassidy, and if you could maybe give a wave, let's thank him. Well, this evening our speaker is Carle Pieters. She is a professor of geological sciences at Brown University, where she has been a faculty member since 1980. She is the principal investigator for the Moon Mineralogy Mapper, which is on the Chandrayaan-1, India's first lunar spacecraft. She also recently received the G.K. Gilbert Award of the Planetary Geology Division of the Geological Society of America as a pioneer in planetary remote sensing. And this is a very well-regarded award in our particular division, so I was very pleased when she was our recent winner. Tonight she will be speaking to us about the Dawn mission on which she is a co-investigator. Carle.
Thank you very much, Jim. And I'm delighted to be here, although this theater is a bit intimidating, I must admit. But it's a pleasure to be here. And I'm going to talk to you today, or this evening, about the early solar system, and in particular the mission Dawn. And Vesta is our first stop. The principal investigator for this mission is Chris Russell. The mission was launched in 2007 and will begin operations shortly at Vesta. I'll have one picture of Vesta to show you that's only a few pixels big now, but this summer is going to be tremendous. We're going to stay at Vesta for a year, studying the planet in great detail. And after the year, we will leave Vesta and proceed to the asteroid series and spend another almost a year there as well. So this is going to be quite a ride, and we're just starting. Before we do, let me introduce you to some of the rest of the team. Shown here is Chris Russell, the principal investigator. He, in fact, is holding a meteorite, a eucrite, which we believe actually came from Vesta. This is a particular kind of meteorite that has the composition that has been identified with remote sensing from telescopes of Vesta. Also shown with Chris there on your right is the deputy PI, Carle Raymond, who really makes sure everything is functioning well. She really interfaces marvelously with the science team and keeps us working very, very hard. They're holding a model of the spacecraft, and you'll see it frequently through my discussion here. Now, of course, we have three primary instruments on the spacecraft, two of which are contributed by foreign national organizations. The framing camera, which has several spectral filters as well, is from Germany. The instrument called GRAND, which is a wonderful acronym, it's the Gamma Ray and Neutrons spectrometer, is developed here in the United States at Los Alamos. And the imaging spectrometer, very similar to the one that I flew around the moon, is contributed by Italy. And these are the people who are responsible for these instruments, or the instrument teams on the Dawn spacecraft. Other couple of key people are Mark Raymond, who is the chief engineer. He has a wonderful blog at the Dawn website, which I'll show you at the very end. If you take any moment or download anything to your iPad or whatever you have, download Mark's blogs. They're just a delight to read. I learn something from them every time I hook into them. In addition is Carle Polanski, who is really in charge of the nitty-gritty, making sure we point in the right direction, when we're pointing, when we should turn on, and we practice that, and it's the kind of things that is absolutely essential to make a mission go, and she's responsible for it. And here's a happy crew on the way to the launch. Now, the science team is just doubled in size, actually, with some participating scientists, but the original science team's about 20 people. And our job is to make sure the science and how we program and work with these instruments actually accomplish what we want them to accomplish, and do it in a very integrated manner. So not only do we have team meetings to discuss this and to work out the plans so that the time that we have when we're at Vesta and at Ceres is well spent, but we also need to do some field work. And Vesta, as you will learn in a moment if you don't already know, is a asteroid that is covered with basaltic material. So naturally we have to go and study volcanic terrains, and one particular that was a delight to explore was in New Mexico. Vesta also clearly has impact craters, and actually I'll show you one that we do know about. Impact craters, rearrange things on the surface of a planet. So this science team went to the Ries impact crater in Germany, sponsored by our German hosts. And you may or may not be able to see it from where you are, but those rocks behind the team members, where they're looking at very closely, are big blocks of different kinds of material all mixed together. It's a wonderful sight to understand the dynamics that go on in an impact cratering event. Our Italian colleagues hosted a meeting for us in Tivoli. Why Tivoli? Well, because that's where the Temple of Vesta occurs. So naturally we had some inspiration during our meeting as well. The main point of showing these images to you is just to remind you that this is a team effort. We have a lot of extremely capable people, but we also have a really good time interacting with each other. And the teamwork is not only important, but it's a real joy. Okay, I'm going to give you a very brief historical perspective now, just because this did not happen just because somebody thought it was a good idea, but it really goes back several hundred years in terms of the giants that programs are built upon. And Tycho Brahe was a key person who in the 16th century really took very careful measurements and itemized where the planets were and how they moved relative to each other. Johannes Kepler later then used these detailed measurements to really understand the orbits of the planets, and he had a pretty good idea that they were how they were oriented relative to each other. And he pointed out that between Mars and Jupiter there seems to be a gap. Then late in the 17th century, Isaac Newton, of course, used Kepler's information to deduce how bodies are drawn to each other in gravitation. That's a fundamental piece of information to planning any of the missions that are exploring outwards in the solar system. And then getting now more towards specifically what we're going to be talking about this evening, a person by the name of Johann Pieters added a little note in a corner of the book that that going from Mercury on out to to Saturn, again, there's this hole between Mars and Jupiter. And when Johann Bode saw this footnote, he added it to his book, and they noted that the relationship between where the planets were positioned in our solar system was very regular, or at least appeared to be regular, and they developed a mathematical equation that predicted where these planets should be, and it fit pretty well, not perfect, but pretty well, except there was this hole between Mars and Jupiter. Well, Franz Xaver von Zach was intrigued by this law and decided to search the sky to look for something in this missing hole. And he got a number of people to help him in this search, one of which was Giuseppe Piazzi, who in January of 1801 saw a dim star that wasn't on his charts that he knew should be there. And when he looked the next night, it had moved just a little bit. Well, unfortunately, he had several events happen that he wasn't able to go back and chart how this apparent movement occurred. But an associate, Gauss, developed some mathematics to try to predict a little bit more. And sure enough, this was discovered a year later, or rediscovered, I should say, and became known as the #1 asteroid, which is Ceres. Now, and that was in 1801. And in 1802, this search continued, and they found the second asteroid, Pallas. And a couple of years later, they found the third asteroid, Vesta, and that was by Olbers, by Harding. And then Olbers in 1807 found the fourth asteroid, Vesta, and that's what we're going to be talking about mostly this evening. And it's interesting to note, in spite of the fact that there was boom, 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 1, 2, 3, 4, it was 38 years before they found another one. So these 4 asteroids are, in fact, some of the larger asteroids in this gap. And Dawn will be going to 2 of them, 2 of the most massive, Vesta first, and then Ceres after we complete our tour of Vesta. So let's talk a little bit more about asteroids, what they are, where they are, why they're there, et cetera, et cetera. And hopefully that will give you a better understanding of why we're doing what we're doing and why we're so excited as the drama continues and as we approach Vesta. Well, first of all, let's step back and we have to think about, well, how did the solar system begin? Well, there was probably a dusty cloud and something happened, maybe a supernova, and this cloud allowed a gravitational collapse, and the star had enough mass so that it turned on, and the material that was in this nebula continued to evolve. The star grew large enough so it was the most massive object in this cloud. But then the remaining material sorted itself out in one form or another. And up in the upper right, you see some of the models of what we think probably happened in our solar system, that you had a star, and that was the hottest part of the nebula, and it got cooler as you went out towards the extremes. Part of that also had a range of the rocks and more metallic, more reduced things are in where the warmer parts are, and the further out you go, you get more volatile rich material. And that seems to hold up pretty good for our solar system at least. And some of the ideas that are currently in vogue really have to do with the transition from the inner part of the solar system to the outer part, where you go from more rocky material that's beginning to come together to more volatile rich material. And what we believe happened, although we're not sure exactly the sequence, is that that transition, that sort of snow line as it's often called, allowed Jupiter to form. Jupiter was able to get a lot of mass and to get pretty big. And that was very important for our solar system. Doesn't mean it's going to be the same way in all solar systems, but for our solar system, it was pretty important. And as you can see from these diagrams, which are really classic diagrams for what probably happened as things started accreting, small things got a little bigger, then got a little bigger, and then they started interacting with each other. And pretty soon, the big things get bigger, the small things become into the big things, and it gets pretty chaotic, pretty violent, actually. And by and large, things sort themselves out into the big bodies, namely the planets, and the solar system is cleared out. Well, there's a couple of models here that are basically showing that the same thing. These are recent models that now are stochastic, namely you start with a small group or a large group of small particles and develop the physics and the interaction of that allows you to predict in a probabilistic manner. Well, what kind of dynamics of interaction will happen, and when will planets come together, and how many planets will form? And because it's random, you have to do this over and over and over again to get any sense of what's common, because every time you run these kinds of models, because there's so much randomness, you'll get a different answer, but the general character is the same, namely that it only takes, maybe 30 million years before most things start sorting themselves out. And after 100 million, 150 million years, things are pretty much over. It happens pretty quick. And as a milestone, what we understand now from looking at the Earth-Moon system, that the event that happened in this period of time where a large body, about the quarter the size of the proto-Earth, hit the proto-Earth, and you probably know this story. That's how we believe the moon eventually formed, from that event. Well, that happened about a little more than 30 million years ago. And then, 100 million years later, it was all over. All this violence was done. And that's an important point in understanding the evolution of the solar system. So these bodies that didn't quite make it into planets are what you really want to know. How was the solar system put together? Well, because of Jupiter, we can study them now. Jupiter, as I mentioned, was probably one of the earlier planets, certainly grew big. And because it was so big, it was able to perturb the material that was between it and Mars, so it could never come together to form a planet. This is a snapshot of the solar system we currently know. You can see the sun and the orbits of the inner planets that you know and love, Mercury, Venus, the Earth, and Mars. And then Jupiter, way out at 5 AU. And all these little dots are the positions of some asteroids. And there's, hundreds of thousands of them now. There's a lot of them. Most of them are very small. But there's a lot of them. But this gives you the pattern. And you see that the large fraction of them occur between the orbits of Mars and Jupiter. You may note that if you see where Jupiter is, there's a sort of a symmetric arrangement around Jupiter, which turns out to be stable positions for some of these small bodies, so they get trapped in those positions. But by and large, they're mostly between Jupiter and Mars. But it turns out here's a diagram that's showing the same thing, but now just statistically giving you a histogram of how many asteroids or small bodies occur at a given location in the solar system, starting at the sun and going out to Jupiter. So you see the little bump over there, which is the ones that are in the same orbit that Jupiter is, just different, displaced around the orbit from it. But you see in this rendition that there are these sort of gaps. Oh, where did that come from? But gaps in the asteroid belt. And those are due to the fact that Jupiter is still massive, and those gaps are what are called Kirkwood gaps, and they're resonances with Jupiter, which means that if Jupiter goes around the sun once, a body in one of those gaps would go around 3 times, and that sets up a interaction between the two, and you can't stay in that position. Jupiter is bigger than you are, and you're sent out. So Jupiter is still perturbing materials within our solar system in these locations. Looking at it a little more closely, you see the sun, where the Earth is, 1 AU, that's our reference standard. Mars is at 1.5. And then the vast majority of asteroids occur between Mars and Jupiter, and the little clump out by Jupiter, the Trojans we call them. But here's some of those resonance gaps. And they're actually very handy, because if there's an asteroid, or if something gets knocked off of an asteroid near one of those gaps, because any object in that position will again resonate with Jupiter and be flung to other parts of the solar system. And by and large, that's the way we get most of our meteorites, either directly from those escape hatches or from larger bodies or small asteroids that were put into there. Jupiter flung them out and sent them in towards the inner solar system, and then we chipped off some pieces a little bit at a time. So this is how we get some material from the part of the solar system that really are part of the earliest parts, the dawn of our solar system, and hence the name of our mission. Shown here is where Vesta occurs in this diagram and where Ceres occurs. So there are 2 very prominent parts of this asteroid belt that will tell us a lot about how it's designed or how it's put together. This is another way of looking at that same plot. Namely, along the axis you have how far it is from the sun, and all those dots are different asteroids now. But instead of just having a histogram, what's shown on the vertical axis is the tilt of the orbit. So some are really flat with the plane of the ecliptic, others are a little tilted. And astronomers really like this kind of diagram, and you can see probably why, because you can see some families, and some of those families probably have some history that's related. Either they were a larger body that had a disastrous event early on, or related in some way or another. But I'll be coming back to this kind of plot when we look more at Vesta and what's in the Vesta environment as well. But first, let's look at comparative sizes. You see Mars and the Moon there for reference size. And the largest object in the middle is the size of Ceres. That's where we're going to after we leave Vesta. And the one in the bright object, sort of in the lower left, is Vesta. Its shape is a little bit, I'll be showing you a little bit better images about the shape of Vesta. But this particular diagram is nice because it shows you the relative sizes of the largest asteroids compared to the Moon and Mars. But it also shows that they're very diverse. This diagram is put together to show that some asteroids are very dark, some are very bright, some of them have round shapes, some of them have weird shapes. They're quite diverse. Some, as you see in the lower left, have a whole clump of asteroids that sort of travel together. Clearly, they're related. So asteroids are not all the same, and certainly Vesta and Ceres we know are going to be dramatically different. For a long time, we thought Vesta was the only asteroid of its type, but as you'll see in a moment, our ideas are beginning to change, and will change more in the next couple of months. But let's move on with the story. What do they actually look like up close? Well, we haven't been to Vesta yet. We're on our way. But we have flown by a lot of asteroids in the solar system with various missions. Only 2 asteroids have we actually stayed at and explored a little bit further. These 2 near-Earth asteroids over on the left there, the largest near-Earth asteroid, in fact, Eros, was visited by a US spacecraft for several months in orbit. And there's another dot to the right of Eros that's in the shadow of that big asteroid. That dot is, and we'll look at it more closely, is the near-Earth asteroid that the Hayabusa mission went to and landed on and brought some samples back, and they've had some wonderful results. So we'll look at these 2 because those are some of our best images of data. But this particular slide shows you the variety and relative size of virtually all the asteroids and small bodies, including comets, that we've been to. And please note the scale bar. That's 100 kilometers. Most asteroids, and certainly comets, are typically very small. 1 or 2 kilometers. The ones shown here are up to 30 kilometers, and the biggest one we have there is on the order of 100 kilometers. But let's look at these 2 near-Earth asteroids in closer detail, because they give us a sense of what we might see morphologically when we get to the surface of Vesta. This is the first, Eros, and it's sort of a peanut-shaped body. It's about 30 some odd kilometers in long dimension. And it's an interesting body, but what's really interesting to scientists is when you get close up, when you actually see some of the details, you see some really weird things like this strip, which is a mosaic. You see some smooth areas on the surface. Well, we don't for a moment think there was volcanism on this tiny body. But it has smooth areas. Somehow it had some process that created a very smooth surface. And what we believe that is an accumulation of a lot of fine-grained dust particles. For whatever process, they're mobile and accumulate in a low-lying area on this planet. This body is something that we're still working the physics of right now. It's a kind of really difficult issue to identify because you can't just put it in an experiment in an Earth-based laboratory. We have too much gravity here. So it's a really interesting issue to address. The other near-Earth asteroid, Itokawa, was visited by the Hayabusa mission from the Japanese space agencies. It's tiny. It's, half a kilometer. You could run across. Well, you can't run across it. You could push yourself across it, maybe. But it's basically a rock pile, but a fascinating one. And you can see there, even this big rock pile has these smooth areas too. So there's something about these kinds of characteristics that we really want to see if we can identify in more detail when we get the kind of sensors that we have operating at Vesta. Now for scale, here's the space station. So this is the relative scale for the Hayabusa asteroid and station. The Japanese were successful in bringing the spacecraft back and getting some really tiny but extremely valuable particles that have clearly identified the character of this material and linking it to a type of meteorite called ordinary chondrite that we have here on Earth. Really a spectacular accomplishment. Okay, Vesta. Why Vesta? Oh boy. Well, Vesta is directly linked to a very unusual type of meteorite. It's one of the few asteroids that we can conclusively say we have meteorites that came from that asteroid. Now, there's a long story behind that, but let me highlight just a couple aspects of it. Shown over on the right are spectra, and I'm not going to show too many spectra, but I'm a spectroscopist. These are wonderful spectra. Those two dips in those spectra, the top one is a telescopic measurement of Vesta from the visible out to the near infrared, way beyond what the visible is, to 2.5 microns. And those two dips are very, very characteristic of a particular mineral called pyroxene. Shown directly below Vesta is a type of meteorite that's measured in the laboratory, same conditions, same spectrum, and you can see it exhibits the same mineralogy. And not only that, we can tell the kind of the composition of the pyroxene that occurs on Vesta based on the meteorites that we have in the laboratory. Fortunately, this was one of the first asteroids measured spectroscopically from Earth, and it turned out to be one of the ones that we could link up with some of the asteroids in our collection. So this asteroid, we're pretty darn sure the minerals, the bulk minerals, the composition of the minerals are identified, and they're basaltic in nature. And basaltic means they were melted once and cooled. And that's an extremely important event. And we'll come back to that in a few moments. Okay, when I say that these are unusual meteorites, well, this is a square pie diagram of the abundance of meteorites. And actually, it's better than a pie diagram, but it's the same concept, namely the area on each of these parts of it represents how abundant that kind of meteorite is relative to all the meteorites that have fallen to Earth. And the little pink area over on the right is the achondrites. Only 6% of the meteorites that fall to Earth have these characteristics that I briefly alluded to, that we understand the mineralogy of and can link it spectroscopically to the asteroid Vesta. 80% of the meteorites are this ordinary chondrite material, which is very similar to what was sampled by Hayabusa, and which we believe also occurs on the asteroid Eros. So that's interesting. Those two near-Earth asteroids really represent 80%, or 80% of our meteorite collections have properties very similar to those two. Then over on the left are some of the most primitive meteorites. They are different. They're quite rare, about as rare as the achondrites, but extremely important because they haven't been processed very much. They haven't gone through thermal or what we call aqueous alteration. So we believe they're some of the most primitive of the primitive materials that still exist in our solar system. And I want to link those two in a moment, specifically in terms of time scale. Shown here is on the horizontal axis is the age, measured by detailed measurements using 5 different techniques in Earth-based laboratories, measuring materials from the meteorites and dating them with great precision. And the very oldest material that's dated is something called the calcium aluminum inclusions, way over there on the left at 4.567. That's easy, 4.567. Remember, 4.567, 0.4567 billion years ago is the oldest solid material in the solar system, in these calcium aluminum inclusions. Well, what do they look like? Well, this is what some of these primitive meteorites look like. And these white globs, those are the inclusions, these calcium aluminum inclusions. They formed before everything else that's in this rock. And this rock, they're a couple millimeters in diameter. They're not big, But they're distinctive, and you can see, and these little round things, these chondrules, people debate how they're formed, but they formed a few million years after the calcium aluminum inclusions at 4.567 billion years ago. Okay, so we sort of have a tie point of when things started to accrete in the solar system, and we have a date for them. Well, what about Vesta? Well, the differentiated meteorites, which I've circled here, these are the meteorites that we can link directly to Vesta. They formed only a few million years later. They're older, but not by much. They formed a few million years, not much, a few million years after the oldest solid particles in our solar system. And these are the differentiated basaltic achondrites. Well, let's come back to this word differentiated, because it's really important, especially for Vesta. What differentiation means to a geologist is that it's a process by which a planetary body or the materials rearrange themselves according to physical and chemical properties. You know, it's well known. You can do it in the laboratory. It's done over and over again in nature. But normally, this differentiation process that allows things to rearrange themselves mineralogically requires heating or melting. You have a lava come up, it comes, it cools, it differentiates. The Earth is differentiated, Mars is differentiated, the Moon is differentiated, Mercury is differentiated. They've all had heating, mostly from long-lived radiogenic uranium, thorium, potassium that has heated and generated heat within the interior of these large bodies. Well, Vesta happened Vesta's differentiation, melting, had to happen within a few million years from the very beginning of the solar system. And this diagram right here is the one we were looking at before. But over on the right, about 30 million years later, it is when this impact event happened into the proto-Earth and the Moon was formed. So bottom line here is that Vesta and its differentiation happened, the melting happened long before anything else, long before the terrestrial planets were even formed. So something in the solar system had to melt these bodies. People believe it probably was a very short-lived radiogenic component, perhaps from a supernova that seeded the early materials of the solar system, melted it early, and then was gone. It didn't melt everything in the solar system, but some parts of the solar system it did melt, and Vesta is one of the key parts of this. So the heat sources that can do this, there's not many. Well, actually, scientists debated this for years and years and years. What could have caused this melting? And the consensus is narrowing it down pretty much. It had to have been these really short-lived radiogenic elements, which again are coupled to the very beginning of our solar system. How our solar system was formed at the very beginning carried with it some of these heat sources that when Vesta got big enough, melted Vesta, and here we have the wonderful basaltic material that we have today. Well, let me show you some pictures that I can show you of Vesta, but these are meteorites. These are this suite of meteorites that have the same compositional markers. They also have markers in the oxygen isotopes, which identify they're all part of the same family. There's three different kinds or flavors, if you will. Actually, there's really only two, and the other is a mixture of those two. The eucrites is one type of material that has two principal minerals, a plagioclase and a pyroxene. The other is diogenites, which is mostly pyroxene with maybe a little olivine, a little plagioclase. And the howardites, which is what Vesta really looks like from the Earth, is a mixture of those two. So most of the surface of Vesta from the Earth looks like a mixture of these materials. But we sort of know what to look for in bulk properties, at least in terms of the rocks that have been able to get to those escape hatches and be thrown to the Earth and we now have them. So we have to be careful that we're not biasing our perception by the little information that we have. Well, let's look at a little bit more. These are the images of Vesta and Ceres from the Hubble. This is the best you can do, and soon you're going to see something much better. But Ceres and Vesta. For Vesta, they were able to have a few sessions where it was studied during a full or a couple of rotations of Vesta. And that allowed a model of Vesta to be developed. And this shows the original data over on the left and sort of the model that is put together with a whole series of these images as Vesta rotates. And then down at the bottom is this model, which is now a topographic model. It's tipped up so you can see what it predicts. And this crater I mentioned earlier, this is what we believe we're going to see, that there's this large depression at the south pole of Vesta, and in the middle of this depression is a mountain. This is a classic impact crater with a central peak that we see on the Moon, on Mars, on Mercury. Here we have it on Vesta, but it's almost as the size of the planet. So what we're hoping is that this has dug deep into the interior of Vesta, and we'll be able to peer inside the interior of Vesta with our sensors. Now, here's a sort of a summary of some of the things that we're going to be looking for. We know basaltic volcanism, the material that's been heated, exists across the surface. We know that from the Earth-based spectroscopy we have. We know we've got this large impact crater at the South Pole. We also know, and this may be obvious to you now, because the spectrum of Vesta that I showed you looked almost exactly like the spectrum of meteorites in the laboratory. That's saying that what's on the surface of Vesta hasn't been changed a lot. It hasn't been altered compared to what we have in the laboratory for the meteorites. That's not true for the samples from the Moon. The soils on the Moon have completely altered the rocks. It's not true for Mars. The rocks from Mars for meteorites look completely different from the soils. But on Vesta, they look the same. So something about the weathering environment at Vesta is different. And at the same time, we also know that from the HST, there's dark and light air. So we know there's going to be diversity. It's going to be fun. Now, the other thing we know, and this comes from telescopic observations, I hope you can see this. On the right, here's that diagram of the distribution of asteroids in the asteroid belt with distance from the sun, and on the vertical axis is the tilt of the orbit. Vesta is that big plus in the middle, but around Vesta, those little red dots are objects that have the same composition as Vesta, namely, and there's some shown over on the left there, with these beautiful pyroxene bands. Not only that, they're stronger than the ones we see on Vesta. These are small asteroids, maybe 10 kilometers in diameter, but they sort of string out from Vesta all the way to these escape hatches, these places where once you reach there, material from there are flung out of the asteroid belt and either out of the solar system or into the inner solar system and perhaps into our laboratory. So we know there's material near Vesta that's probably related to Vesta, and somehow, and what most people believe is that sometime an event happened on Vesta, perhaps the event that created this enormous crater at the South Pole, and sent these 1 to 10 kilometer size vestoids, they're affectionately called, surrounding Vesta and to some of these escape hatches that send some of the meteorites down to Earth. So this we know and we're expecting. So a couple of major questions. Did a major impact event create these vestoids? We think it probably did, but that's a hypothesis. We'll have to look for evidence to see if that's the case. Equally important, when did it happen? Did it happen recently? And that would explain why things look so fresh now. Or did it happen long ago? And we have to find some other reason why the surface of Vesta looks so undisturbed. These are mysteries that we don't have answers for, but certainly we're eager to use our tools to investigate. Another question is, did this melting event, which differentiated Vesta, did it drive off all the volatiles? Originally, we would have said, of course it did. Anything that's going to melt this body is going to drive off every volatile. But we've learned from our lunar case that, well, on the moon, on the superficial part of, the outermost surface of the moon, there is OH and H2O. This is, again, some of the results from the spectrometer on Chandrayaan. And it shows that a silicate surface in a space environment, the silicates which have oxygen, hydrogen from the solar wind, can get together and form OH and H2O. Again, this is a hypothesis, but if this hypothesis for the origin of this water is correct, then it predicts we should see the same thing at Vesta. And we have the right spectrometer to do it. So we're looking forward to testing that and see. It will be less because Vesta's further out and the solar wind will be weaker, less hydrogen, but enough to look for. Okay, what will we do? And now I should move along, so we'll have a little time at the end to chat. Well, this is a little map of how we got to where we are now. We launched in September '07, and we're using a propulsion system that most of you are probably not familiar with. It's called ion propulsion. It's not a chemical rocket that you just burn and you're gone. We got out of the Earth's environment that way. We did take a rocket up and got out of the Earth's environment. But then we turned on our little motors, which are ion propulsion, which is just a little gentle. What it does is it takes an element, xenon in particular, and massive solar panels, and ionizes xenon and accelerates them between two electrically charged plates really fast, so they leave the spacecraft really fast. That's what you see coming out here. That's not a lot, but you do it constantly, and you can see the little blue lines here. That's when we're thrusting. That's when we're sending these ions out constantly. So you do it a long time, and you get going pretty fast. So you can see about half the time we're thrusting, and what we're doing is we're just gradually matching our speed up to that of Vesta. And when we get to Vesta, I'll show you in a moment, pretty soon, instead of having to fire our rockets and enter into orbit, pretty soon Vesta will be big enough to capture us. And we'll just sort of spiral around. And then we'll use this to sort of tweak our orbit and put it just where we want it to be. It's going to be a great trip. Here's our timeline. We're at about now is when we should be getting down images that's pretty much comparable to the HST images. And in about a month, we'll be about 5 times the resolution of HST. And you can be sure there's going to be a nice press conference that will show our beautiful data at that point. I wish if this was a few months later, I would be able to show it to you, but you'll just have to wait. This approach has lots of planned image sequences that will allow us to get data, to make sure everything's working properly, and to get a first taste of what we're going to be doing when we're in our mapping orbit phases. The first mapping sequence starts in August from a orbit, which we're calling the survey orbit, which will be a regular mapping orbit where both the spectrometer and the framing camera will map the entire body. On the way there, right in the middle, or a third of the way over on the left, we will pause and do using our framing camera, do a deep search of space to make sure or see if there's any satellites out there. So we'll need to know, and we'll want to know, if there's any satellites of Vesta in the environments, not only for safety purposes, but obviously for scientific purposes. Here's the only picture of Vesta from dawn that I can show you. And this was taken almost a month ago. So I know it's better than this already, but I just can't show it to you. But there will be a lot of data very soon, certainly by the end of the month, that will be thrilling. I guarantee it. But for us, after all these years, this is thrilling. We see Vesta in our instruments. You know, these photons are from Vesta. We're just getting closer and closer, and it keeps getting better. This is sort of the timeline that we'll be accomplishing in the next couple of months. Again, the bright blue is when we're thrusting. The dashed line is when we're pausing and doing things. So you can see we're sort of thrusting, and around middle July is when we're getting close enough to Vesta that basically Vesta's capturing us. We will spiral around Vesta, and we will be using the thrusters then to really get that into a circular orbit. It'll take a while, as you can see, about a month to get into our survey orbit. But it's not a one-shot deal. It's a pretty gentle sort of maneuver. And from August on, we will go through 3 major phases, what we're calling survey, which is the high altitude. Then we'll use the thrusters to bring us down to a lower orbit, and we'll stay there for a long time because we have a lot more data to get at the lower altitude. Then we'll again use the thrusters to take it down to a lower orbit and spend as much time as we can down there. The lowest orbit is needed for the gamma ray spectrometer, which needs a lot of counting time. So we're hoping we can spend enough time down there to get really good statistics on the elemental abundances. Here's the sort of perspective of the 3 orbits that will be working for our science analyses, the survey, what we're calling HAMO, LAMO, high altitude, low altitude. We'll be measuring all the physical properties, including gravity, topography. We'll be using the cameras and the spectrometer measure the mineralogy and all the morphological properties, and the gamma ray neutron spectrometer to measure the elemental abundances, with all of us eager to look at the impact history, the volcanic history, the crustal evolution, peer into this big hole on the south, and to understand the weathering environment on Vesta. Well, what might we find? And I'm just going to show you a couple of purely conjectures. I may be completely wrong here, but what are some of the things we might find? Well, we might find a really, really old surface that's heavily cratered. It's been there for 4.5 billion years. It's been exposed longer than the lunar highlands. Remember, the moon was formed after Vesta. So it could be really, really battered and old. But then we know it's sort of a fresh-looking surface. So maybe there's something that's refreshened it. Maybe a lot of little craters. Maybe a comet came by and refreshed the surface for something. Alternatively, maybe this impact that created the Big South Hole or some other impact spread debris over the entire surface that's recent. Well, we don't know, but we'll be able to tell that with the sequence of detectors that we have. It'll probably be none of the above. It'll be something I can't think of. We'll find out. One thing that we all are really eager to find out about is this big hole, at the big crater at the South Pole. We're pretty sure that's going to give us some interesting data. What we don't know is whether Vesta has remained intact in its differentiated form for 4.5 billion years, and we'll be able to peer in and see different layers of the upper crust and maybe even into the mantle, or if it's going to be all jumble or something else. Again, we don't know. But this area we're really going to be spending a lot of time looking at. And of course, what's probably going to happen is, well, with that, thank you.
Well, thank you, Carle, for a very interesting lecture. And once again, we want to thank Aerojet and NASA for making this possible. We apparently don't have the planetarium outside open. That's weather dependent, and I just got the sign that apparently there isn't something to look at out there. I do want to remind you that later this month is Become a Pilot Day out at the Udvar-Hazy Center, another part of our Air and Space Museum. And if you're into Twitter, just look for Air and Space to get the information about that. Please don't forget to turn in your surveys as you leave the theater. And one of you will be a lucky winner of a door prize if you turn in your survey. But now for at least a few minutes, we can answer questions. And what we'll do is I will try to summarize and repeat the question for the videotape. So try and make them not real long so I can get what you're asking about. Yeah.
Real quick question. Your orbits, are they going to be polar or equatorial?
Are the orbits polar or equatorial?
Principally polar. The orbits are designed to cover the whole planet as it rotates, but it's a little tilted too, but we will cover the entire planet. One thing relative to that, although you didn't ask the question, let me answer it, is that when we arrive at Vesta itself will be pointed a little so that the North Pole will be in shadow. That's the bad news. The good news is the South Pole will be lit. And as we're there, it will gradually straighten up, and we're hoping before we leave, the North Pole will be lit, so we'll be able to see it too.
Yeah.
Vesta's gravity must be just a tiny, tiny fraction of the Earth's or even the moon's. If it's scooting along all these millions and billions of miles to get there, how does it slow down to the point where Vesta is able to capture its distance?
How does something the size of Vesta capture the spacecraft with its limited gravity?
Well, I asked that very question to our engineers because again, we're all thinking we got to get to the moon or Jupiter or wherever, and you got to slow down when you get there. That's not the way it works for Vesta because we're just gliding up. We're really just getting close enough such that we are captured gravitationally. We don't have to fire a rocket to slow down. All our thrusting is so that we're matching our speed with Vesta's. And if we have the same orbital velocity as Vesta, that means we're in the same orbit. And when we're close enough to Vesta, we're captured. If we didn't do anything, we'd have a sort of a weird loop. So we use the thrusters to get the kind of orbit we want around Vesta. But it's a completely different approach than what you're normally used to.
Yeah.
What was your motivation or thought process to start this mission?
What was the thought process behind Dawn?
Well, it's in the name, Dawn. We want to understand the earliest history of solar system. And both Vesta and Ceres is a whole nother lecture. It's going to be quite different. It's going to be icy. Are some of the last building blocks of the earliest part of the solar system. And we had an opportunity to go and try to find out more about those building blocks of the solar system.
You mentioned that Vesta had been melted and that so had other objects in the universe. Do we have a good enough sense of that to know if there's a larger pattern?
Vesta was melted, but is there a pattern to melting in the solar system?
In the large planets, yes. All the rocky planets have gone through differentiation. But that's largely because they have so much material and the heat-forming elements, but these are the long-lived, uranium, thorium, are enough to allow their internal engines to differentiate. Vesta is unusual, and what we don't know is how many of these small bodies melted really early. We're beginning to suspect now that much of the inner part of the solar system, remember that one diagram that had all these things moving around and eating up each other, that we suspect now that because what we see at Vesta and what we're beginning to understand about these short-lived elements, that some of the inner part of the solar system may have melted earlier too. But we don't know that yet. That's something that's still being pursued.
How about way in the back?
Were there any compromises to, or was it just out of range to actually land and take physical samples, and even better, bring some back?
Was there a possibility of landing and bringing a sample back?
Would love to do that. It's hard to do because not only do you have to get there, getting back is really hard. And actually, to do what we're doing at Vesta, and certainly even going on to Ceres, we couldn't have done with chemical propulsion. So even what we're doing is really using the new technology to do something new. To bring samples back, the Hayabusa mission did, but they were able to accomplish that because they went to an asteroid that's close to Earth. It wasn't in the main belt, it's close to Earth. And you can do that, it's hard, but you can do it if it's something real close, like a NearEarth asteroid or the moon.
The diagram of the different layers of Vesta possibilities. In the conglomerate diagram, there seems to be a mantle there, whereas in the non-conglomerate one there wasn't. So would there be a possibility of both mantle and if it was not a conglomerate, something there not being visible?
He's asking if there is the possibility of a mantle in Vesta.
Good eye. Actually, we don't know. We made up that diagram. But what we think probably is, or there, what probably, maybe 20%, 30% probable, we know it differentiated. We don't think that even in the most severe impact environment, it broke up completely and got put back together. And so we think there's still something that's original core or core and mantle, but we don't know how much. So I think even in a worst case, you probably have some residual core and some debris on top. Now, could there be a liquid core? Probably not, because it's too small. But that's just a probably.
Being over visiting the Natural History Museum, we learned that iron nickel meteorites were formed with a very slow cooling. That is to say, on the order of a degree Celsius per million years. What is the likely source of the nickel iron meteorites that we see in the Natural History Museum?
He's asking about iron-nickel meteorites that have a long cooling history, and where did they come from?
Oh boy, yes, you've got one of the fundamental questions that planetary scientists are still grappling with. Most people believe, as I'm sure you probably learned, that these materials had to have melted early, probably in this early part that I was talking about, but because they were cooled slowly, it means they had to be inside something bigger. And the fact that we have that sample now means that bigger body is no longer there, means it got broken up. So what part of the debris out there are these pieces? We don't know. Astronomers have looked for asteroids that could be these metallic cores. There was a time where we thought we knew one class of asteroids would be them, but it turned out when you look at it with other sensors, they don't hold up. There is one, I think, that the radar data have confirmed that's likely to be a metallic core, but how you identify enough meteorites to account, enough parent bodies to account for the diversity of these core elements that we have now in our collection is a real problem. We don't know enough.
You mentioned that you use chemical propulsion. What did the ion propulsion apply to?
What's the distinction between ion propulsion and its advantage over chemical?
It's just more efficient, and we don't have to take as much fuel to get the total amount of what's called delta V, the total getting from here to there. It does take us longer, but that's no problem.
The answer to that question is that when you go thrust propulsion, you're matching the speed, orbital speed of the orbit that counts. You're out on an orbit that has an apogee aspect, and the parent being down much lower. You're not I've done this work in the past, so
Good.
I'm very interested in that aspect of the vision, and I'm wondering if some of the stuff you showed us on the screen is available on the websites, or we can get it from JPL, or could you...
The web app. He's asking, is some of this on the web already? And the
Yes, yes. In fact, many of the figures I pulled off of that.
I assume that JPL is doing all of the mission observations, the trajectory.
Yes, JPL's doing the management and the operations. And
Pris just pointed out that this lecture itself will be available on the website. If you want to review what she has been talking about and some of the pictures, you can see it on our NASA website shortly. So, how about towards the back of you?
When you discover some of these things that you are going to find out that stuff, like you expect to see that giant crater in the southern hemisphere, do we have a nomenclature for naming these things? Because there are going to be a lot of discoveries made fast and furious, and just calling them crater 1, crater 2 will get confusing. So do we have a way of naming all these things we're going to discover there?
Is there a system for nomenclature for naming these things as we discover them?
the last two science team meetings, we talked about that in great detail. And the answer is yes. I can tell you that the Big South crater is likely to be called Ria Silva. There's a procedure, a formal procedure with the IAU that needs to be adhered to for formal naming of features. And we've arranged with this organization to have the type of names which will be associated with Vesta, Vestal virgins, etc., for some of the major features. Now, you don't name all the features. Typically, you name some of the most prominent, and then letter designation nearby to them. But we will, when we first get to Vesta and start looking at each section of Vesta, we've agreed sort of on a mapping strategy that will basically give a number, a location, a feature name, and a number, like a certain location, crater 1, certain location, volcano 2, so that we'll have something so we can at least talk to each other about the same features. And then those that end up being most prominent will submit for formal names.
How did you choose the sensitivity range for the spectrometer? And once you get to Vesta, how are you going to calibrate?
how was the sensitivity chosen for the spectrometer, and how will you calibrate it?
Well, the most important decision is what wavelength range to use. And that's selected by understanding where signatures are in rocks and minerals. And the visible up to the near infrared. Actually, the sensors that are used go out to 5 microns, which is nice because it allows us to go through the water bands, and there's a few organic bands that are in that as well. So it's a really nice sequence. That's one of the prime criteria. The second, of course, is what detector technology is available. And in this particular case, they matched well. I think, was there another part of that question?
Calibration.
Oh, calibration. The first is, of course, you do very serious calibration on the Earth before you send it. We did a flyby to Mars, which was intended to be a calibration sequence. And for the framing camera, we were able to use Mars because it's an extended source to get basic calibration. And that turned out very good. Unfortunately, for the spectrometer, there was some issue that we weren't able to turn it on at the right time, or some hiccup in the sequencing happened. So we didn't get Mars data for the spectrometer. So Vesta, as we're approaching, will be our first look at an extended source with the spectrometer. We've looked at stars, but stars are a pinpoint, and we want to look at the spatial extent. So it's a more complicated procedure. But we'll use mostly the ground calibration for the initial.
Last question, way in the, yeah, you with your hand up there.
On the graph showing the distribution of the Vestoids, there was one, I think, called Magnia, which was way off in one quarter. Could you comment on its remove?
He's asking about in the Vestoids, there was one way off of the diagram on the side of the diagram.
That's puzzled us for a while. As I mentioned a while ago, for a long time we thought Vesta was the only major body that differentiated and survived. You know, there's a lot of these that have been broken apart, but Vesta was the big one that survived. And that all are basaltic achondrites because they had the same characteristic came from Vesta. And when we saw the Vestoids, we saw, oh yeah, everything fits together, it's a nice story. But there's this one way out, and not only is it way out, you have to go through a couple of these escape hatches. So you can't just toss something out and get it out there. So it's certainly beginning to be a strong case that there was more than one body that differentiated. And that's all we know for now. It's a very important issue. Most of the material further out in the asteroid belt are more primitive in character based on their signature telescopically, but this one is not. It's unusual.
Well, thank you all for very good questions, and we hope to see you all again for the 2012 Exploring Space series.
And there's a